Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
David Ruelle's intellectual journey unfolded against a backdrop of profound transformations in the mathematical landscape. His early fascination with the intricate dance of chaos and order, a dance often obscured by the apparent randomness of nature, would ultimately shape his remarkable contributions to the field of dynamical systems theory. His career commenced with a quiet, persistent curiosity about the hidden mechanisms driving seemingly unpredictable phenomena. The year was 1958. As young, ambitious mathematician, David Ruelle found himself immersed in the burgeoning world of mathematical physics. The atmosphere was charged with an almost palpable sense of intellectual ferment. The very nature of reality, once seemingly fixed and predictable, was now being viewed through a new lens. Quantum mechanics, a revolutionary theory, had shattered the classical Newtonian world, revealing a universe governed by probabilities and uncertainties. The echoes of this revolution reverberated through the halls of academia, inspiring a generation of thinkers to seek deeper understanding of the complex systems that govern the universe, from the motions of stars to the turbulent eddies of a flowing river. Ruelle's initial work involved the meticulous study of specific, often seemingly trivial, problems. He sought carefully, methodically, to understand the limits of existing paradigms. This approach, a hallmark of his later work, was a testament to his belief in the power of detailed analysis. He sought to embrace the complexities of the world, to unravel their intricate threads. This approach was crucial in navigating the intellectual terrain of the 1950s and 60s. The mathematical tools available were, while powerful, often inadequate for tackling the complexity of systems, displaying chaotic behavior. Existing theories struggled to reconcile the apparent predictability of simple systems with the seemingly random fluctuations of complex ones. Ruelle remained undeterred. He was drawn to the challenge of understanding the mechanisms behind such apparent unpredictability, to uncover the underlying order hidden within the chaos. This early focus on specific problems, on the precise mathematical structures governing these systems, served as a testament to his deep understanding of the power of focused inquiry. He recognized that comprehensive understanding often emerges from the meticulous study of individual components, a process he found more effective than a sweeping, generalized approach. His work, rooted in the rigorous traditions of mathematics, drew deep influence from the burgeoning field of physics. The quest to understand the fundamental laws governing the universe, from the smallest particles to the largest structures, was attracting mathematicians to the study of physical systems. This interdisciplinary approach became an essential component of Ruelle's research, constituting a true integration. His ability to bridge the gap between mathematical rigor and physical intuition would become a defining characteristic of his contributions. Ruelle's early contributions, characterized by a unique combination of rigor and insight, held a significance that transcended immediate sensation. He sought to develop new mathematical tools, crafting new lenses through which to view these intricate systems, demonstrating a drive beyond applying existing ones. This approach, a hallmark of his later work, was a testament to his profound understanding of the limitations of existing methodologies. The significance of Ruelle's work extends far beyond the realm of pure mathematics. His work on dynamical systems has profound implications for understanding a wide range of phenomena in the natural world, from the complex patterns of weather systems to the turbulent flows of fluids. The chaotic behavior of these systems is becoming increasingly relevant to our understanding of the world around us. His insights hold the key to unlocking the mysteries of these complex systems, a key that will undoubtedly prove invaluable in the years to come. His work holds the potential to revolutionize our understanding of the universe around us. David Ruelle's contributions to dynamical systems theory represent a profound shift in our understanding of complex, unpredictable systems. He sought to develop new frameworks, new lenses through which to view these intricate systems. This ambition, a hallmark of his later work, was a testament to his profound grasp of the constraints inherent in prevailing methodologies. The study of dynamical systems, concerned with the evolution of systems over time, had already yielded valuable insights into predictable behavior. Newtonian mechanics, for example, provided a framework for understanding the trajectories of planets. Yet, many natural phenomena, from the swirling eddies in a turbulent fluid to the unpredictable fluctuations in weather patterns, defied such deterministic predictions. These systems, characterized by their sensitivity to initial conditions, exhibited a seemingly random, chaotic behavior. Existing mathematical tools struggled to grasp this complexity. Ruelle, recognizing these limitations, embarked on a quest to unravel these chaotic systems. He tackled the challenge of understanding how seemingly simple rules could give rise to such complex and unpredictable behavior. He recognized that the underlying equations governing these systems possessed a hidden complexity that manifested as intricate patterns and unpredictable trajectories. His work aimed to illuminate this inherent complexity. A crucial concept that emerged from Ruelle's exploration is that of strange attractors. These intricate fractal-like structures govern the system's long-term behavior. They possess characteristics far exceeding those of static points or simple closed curves. They represent the set of all possible long-term states that the system can occupy, a collection of points in phase space toward which the system's trajectory evolves. This concept offered a powerful tool for understanding the underlying mechanisms driving chaotic dynamics. It provided a concrete analytical framework. Ruelle's work on strange attractors illuminated the intricate dance between order and chaos. Consider, for instance, the Lorentz equations, a set of simple differential equations that model atmospheric convection. These equations, while appearing straightforward, can exhibit remarkably complex behavior. Ruelle's analysis using the concept of strange attractors revealed the presence of intricate patterns and unpredictable trajectories within these seemingly simple equations. This provided a framework for understanding the intricate patterns in seemingly chaotic systems. Ruelle's work holds significant implications for various fields. His insights into strange attractors have profoundly impacted our understanding of weather patterns. The intricate dance of air currents, pressure gradients, and temperature variations creates a system that exhibits chaotic, unpredictable behavior. Ruelle's work provided a means of understanding the underlying mechanisms driving these intricate patterns. It served as a practical analytical tool. This understanding, in turn, has implications for weather forecasting, allowing for more accurate predictions and a deeper appreciation for the inherent complexity of these systems. Ruelle's insights inform our understanding of turbulence, another manifestation of chaotic behavior. The swirling eddies and chaotic motions in fluids, from the flow of water in a river to the turbulence in an airplane's wake, are governed by complex interactions. Ruelle's work, by introducing the concept of strange attractors, provided a framework for understanding the patterns within the seemingly random behavior. This understanding has implications for engineering applications, allowing for improved designs of aircraft and other systems that operate in turbulent environments. Furthermore, Ruelle's work has implications for a wide range of other phenomena, from the oscillations of biological systems to the fluctuations in financial markets. His insights into dynamical systems have the potential to unlock new understandings of these intricate processes. His emphasis on the interplay between order and chaos has opened up a new perspective on the inherent complexity of the universe. This perspective contributes significantly to a more nuanced understanding of the world around us. Ruelle's approach involved the development of new tools. This innovative spirit is a defining characteristic of his work. He described the behavior of these systems and sought to understand the fundamental mechanisms driving this behavior. His approach, characterized by meticulous analysis and a profound understanding of the limitations of existing methods, has profoundly influenced the field of dynamical systems theory. This approach has profoundly impacted our understanding of the natural world. His work has established a new paradigm for understanding the intricacies of complex systems. It has opened doors to new insights, new discoveries, and a more profound appreciation for the inherent complexity of the universe. This profound understanding has the potential to revolutionize our understanding of the universe around us. His insights into the nature of chaos through the concept of strange attractors have transformed our understanding of a vast range of phenomena. These insights possess a tangible impact on our ability to model and predict the behavior of complex systems. The intricate dance of chaotic systems, revealed through the geometry of strange attractors, offer profound insights into the unpredictable evolution of relatively simple deterministic models. This exploration of complexity extended naturally to systems comprising vast numbers of interacting components. The fundamental concern of statistical mechanics, understanding how macroscopic properties emerge from the collective behavior of countless particles, presents a formidable intellectual challenge, a challenge connected to the dynamics of low-dimensional systems. Statistical mechanics traditionally excels at describing systems in equilibrium, where properties like temperature and pressure are uniform and time-independent on average. The powerful framework developed over centuries, leveraging concepts from probability and thermodynamics, provides a comprehensive picture of such states. However, the universe teems with systems far from equilibrium, fluids flowing, heat conducting, chemical reactions proceeding, biological processes unfolding. These non-equilibrium phenomena represent the dynamic, ever-changing reality we inhabit. Physicists and mathematicians in the mid-20th century grappled intensely with formulating a rigorous general theory for these non-equilibrium states. Equilibrium statistical mechanics rests on the principle of maximizing entropy under constraints, yielding stable, well-defined distributions. Non-equilibrium systems, however, continuously dissipate energy and produce entropy, maintaining their state through fluxes of energy and matter. The mathematical tools available often lack the capacity to handle the time evolution and spatial variations inherent in these systems with the same level of rigor achievable for equilibrium. Establishing fundamental results, such as the existence and properties of steady states or the behavior of fluctuations around them, remain particularly elusive. The field needed a robust mathematical foundation providing rigorous methods. David Ruelle brought his characteristic precision and deep analytical skills to bear on these complex problems. His work provided crucial mathematical underpinnings for understanding non-equilibrium statistical mechanics, much as he had done for dynamical systems. He recognized the need for a framework that could describe the statistical properties of systems driven by external forces or boundary conditions. A significant part of his contribution involved extending rigorous methods from equilibrium statistical mechanics to analyze non-equilibrium phenomena. He delved into the mathematical structure of phase transitions, a concept central to equilibrium physics, like water boiling or a magnet losing its magnetism. Equilibrium phase transitions involve changes in the system's ground state or symmetry breaking. Non-equilibrium systems exhibit transitions to entirely new types of complex behavior, such as the onset of turbulence in a fluid flow. Ruelle's work helped establish a more rigorous understanding of how such transitions could be described mathematically within a statistical framework. He made fundamental contributions to the theory of equilibrium states for infinite systems, crucial groundwork for extending analysis to the non-equilibrium domain. His results on the existence and uniqueness of equilibrium states, particularly in the context of lattice systems and continuous systems with short-range interactions, provided a solid foundation. This rigorous understanding of the equilibrium case then informed his approach to the non-equilibrium scenario. His analysis of distributive systems, directly linking back to his work on dynamical systems, proved especially insightful. He demonstrated how the long-term behavior of certain non-equilibrium systems could be described by attractors in the state space, similar to those found in chaotic dynamics. For systems with many degrees of freedom, these attractors exist in infinite dimensional spaces. Ruelle explored the statistical properties of the motion on these attractors, suggesting that even far from equilibrium, a statistical description could be possible, characterized by invariant measures on the attractor. This offered a powerful conceptual bridge between the microscopic dynamics of many particle systems and their macroscopic statistical behavior away from equilibrium. He explored the mathematical properties of these non-equilibrium steady states, which represent time-independent probability distributions for systems driven out of equilibrium. Establishing the existence and characterizing the properties of these states is a major challenge. Ruelle's work, often in collaboration with others, provided rigorous results concerning these states, particularly the relation to concepts like entropy production and the fluctuation dissipation theorem, which connects the response of a system to small perturbations to spontaneous fluctuations in equilibrium. Extending such relationships to non-equilibrium states required significant mathematical innovation. The innovative aspect of Ruelle's approach lay in his unwavering commitment to mathematical rigor. Statistical mechanics, particularly non-equilibrium statistical mechanics, frequently relies on physical intuition, approximations, and numerical simulations. While essential for progress, these methods can sometimes obscure the fundamental mathematical structure. Ruelle insisted on formulating problems precisely and proving results rigorously, employing advanced tools from functional analysis, probability theory, and the theory of dynamical systems. He sought to establish under what mathematical conditions certain physical phenomena could occur and what the precise mathematical properties would be. This provided a level of certainty and depth of understanding previously uncommon in many areas of the field. Consider the problem of heat conduction. Microscopically, this involves complex interactions between particles. Macroscopically, we described it with Fourier's law, stating that heat flux is proportional to the temperature gradient, with a proportionality constant called thermal conductivity. Deriving such macroscopic laws from microscopic dynamics for non-equilibrium steady states and proving their validity rigorously is exceedingly difficult. Ruelle's work contributed to the mathematical framework needed to tackle such problems, providing insights into the conditions under which macroscopic transport laws emerge from microscopic interactions. His influence on statistical mechanics has been profound. He helped solidify the mathematical foundations of both equilibrium and non-equilibrium theories, inspiring a generation of researchers to pursue rigorous approaches. His work on phase transitions, attractors, and distributive systems, and the mathematical structure of non-equilibrium steady states provided essential concepts and tools. He demonstrated that even the complex, time-dependent behavior of systems far from equilibrium could be subjected to deep mathematical analysis, opening up new avenues for theoretical investigation. The relevance of Ruelle's contributions extends directly to contemporary scientific challenges. Understanding complex systems comprising vast numbers of interacting components driven by external forces and far from equilibrium is central to many modern fields. Climate change modeling, for instance, involves simulating the behavior of the Earth's climate system, a quintessential non-equilibrium system with countless interacting components including atmosphere, oceans, ice, and biosphere, driven by solar radiation. While climate models are complex numerical simulations, the underlying theoretical frameworks for understanding the statistical properties of such large, driven systems benefit from the foundational work Ruelle pursued. Concepts related to non-equilibrium steady states, the emergence of macroscopic properties from microscopic interactions, and the statistical description of complex distributive systems are directly applicable. His work finds resonance in fields like climate science, fluid dynamics, particularly the study of turbulence, a highly complex non-equilibrium phenomenon, plasma physics, materials science, understanding driven materials, and even theoretical economics, where large numbers of interacting agents create complex non-equilibrium dynamics. The rigorous mathematical perspective he championed provides essential insights into the fundamental nature of these systems. The transition from understanding the geometry of chaos in low-dimensional systems to formulating mathematical principles for the statistical behavior of systems with infinitely many degrees of freedom in non-equilibrium states marks a significant expansion of Ruelle's intellectual reach. He applied the same commitment to rigor and deep conceptual insight to both domains, revealing underlying mathematical structures that govern complexity across vastly different scales. His work in statistical mechanics, building upon and complementing his contributions to dynamical systems, provides a powerful lens through which to view the intricate, dynamic world around us, establishing a framework for rigorous analysis where previously only approximations prevailed. This relentless pursuit of mathematical clarity, applied to some of the most challenging problems in physics, defines his enduring legacy in this field. His theoretical explorations related to the evolution of systems, whether few-particle or many-particle, laid crucial groundwork for the development of robust mathematical models. The challenge of describing the long-term behavior of systems exhibiting chaos demanded the development of entirely new mathematical frameworks. These systems, while deterministic, require prediction methods effective beyond very short timescales. As traditional approaches prove insufficient, their trajectories diverge exponentially, precluding precise forecasting. The core problem resided in finding a way to characterize the overall structure and statistical properties of the complex sets in phase space that these chaotic systems explore over time. Sets often referred to as strange attractors, tracking individual paths, yielded limited insight into the global dynamics. A different perspective was needed, one that could capture the intricate, often fractal geometry of these attractors and the statistical distribution of trajectories upon them. David Ruelle addressed this profound challenge by championing the application of sophisticated mathematical tools, adapting and extending concepts from other domains to build a rigorous analytical structure for chaos. His approach involved abstracting the behavior of the system, developing combinatorial and scaling perspectives alongside the analysis of individual differential equations or iterative maps. This marked a significant evolution in the mathematical study of dynamical systems, providing the foundational language to discuss chaotic phenomena with precision. One powerful avenue he explored involved the use of symbolic dynamics. This technique translates the continuous evolution of a system into a sequence of discrete symbols. Imagine partitioning the phase space of a dynamical system into a finite number of regions. As a trajectory evolves, it passes from one region to another. This sequence of region visits can be recorded as a sequence of symbols, one symbol representing each region. The infinite trajectory in continuous space becomes an infinite sequence of symbols. The genius here resides in the fact that for certain types of systems, particularly those exhibiting hyperbolic chaos, there exists a close relationship, often a topological conjugacy or a semi-conjugacy, between the dynamics in the original phase space and the symbol dynamics on the space of symbol sequences, such as a shift map. Ruelle brought a new level of rigor to the application of symbolic dynamics in this context. Previous uses might have been more illustrative or limited to specific, idealized systems. He demonstrated how symbolic dynamics could be used to prove theorems about the structure of strange attractors, to understand the distribution of periodic orbits, and to calculate invariant measures, the probability distributions describing where a typical trajectory spends its time on the attractor. The space of symbol sequences, equipped with a natural metric, becomes a mathematically tractable object. Properties of the chaotic system, like sensitive dependence on initial conditions, manifest as properties of symbol sequences, like the rapid divergence of sequences corresponding to nearby initial points. This transformation from a continuous problem to a combinatorial one opened up a wealth of new analytical possibilities. Consider the geometric complexity of a strange attractor. It possesses structure at arbitrarily small scales, often exhibiting self-similarity. Traditional analytical tools struggled with such intricate geometry. Symbolic dynamics provided a coarse-grained yet powerful way to encode the structure. They allowed sequences of symbols reveal the topological structure of the attractor, while the frequency of specific symbol blocks relates to the invariant measure. Ruelle's work helped establish how one could rigorously translate questions about the dynamics on the attractor into questions about the properties of these symbolic sequences. This provided a concrete, formal method for studying objects whose visual complexity defied conventional description. Another crucial set of tools Ruelle integrated into the study of chaos derived from the renormalization group, a concept originating in statistical physics and quantum field theory. Renormalization group methods involve examining a system at different scales and looking for scaling properties or fixed points under scale changes. In the context of dynamical systems, these methods are particularly useful for understanding phenomena like period doubling cascades, a common route to chaos. As a parameter in a system is varied, a stable periodic orbit can become unstable, giving rise to a new stable orbit with double period. This process can repeat, leading to an infinite sequence of period doublings accumulating at a critical parameter value where chaos emerges. The sequence of bifurcations in a period doubling cascade exhibits remarkable universality, meaning the scaling factors between successive doublings are the same for a vast class of systems, irrespective of their specific equations. This universality strongly suggests the presence of underlying structure that transcends the details of the particular model. Renormalization group provides a mathematical framework to explain this universality. One defines a transformation on the space of dynamical systems that corresponds to iterating the system twice and rescaling the variables. The universal scaling factors are related to the properties of a fixed point of this renormalization transformation. Ruelle, along with collaborators, applied and formalized these renormalization group ideas within the rigorous mathematical framework of dynamical systems. They investigated the mathematical properties of the renormalization operator itself, studying its fixed points and linearized behavior around these fixed points. This rigorous analysis provided a deep explanation for the observed universality in period doubling cascades and offered insights into the transition to chaos. It demonstrated how scaling symmetries, previously understood in the context of critical phenomena and phase transitions, played a fundamental role in the onset of complex dynamics. The combination of symbolic dynamics and renormalization group techniques, among others, represented a significant advance in the mathematical understanding of chaos. Symbolic dynamics provided a powerful way to encode the topological and measure properties of strange attractors, simplifying the analysis of their intricate structure. Renormalization group offered a framework for understanding the scaling properties and universality observed in transitions to chaos, revealing deeper mathematical symmetries underlying complex behavior. Ruelle established the rigorous mathematical foundations for applying these tools in this new domain. He provided theorems and definitions establishing formal proofs about the nature of chaos. Building upon heuristic arguments and numerical observations, his theoretical work deeply influenced the development of mathematical models for the evolution of systems. By providing rigorous tools to analyze the long-term statistical behavior of chaotic systems, his work allowed researchers to build models that could capture essential features of complex phenomena in fields ranging from fluid dynamics to climate science, where chaotic behavior is ubiquitous. The ability to characterize strange attractors using dimensions, Lyapunov exponents, and variant measures, all underpinned by the rigorous frameworks he helped establish, enabled a more quantitative and predictive approach to systems previously deemed intractable. Understanding the properties of the attractor itself and the statistical distribution of states became central, acknowledging the impossibility of predicting individual trajectories far into the future. This change in perspective, facilitated by the rigorous mathematical tools he developed and promoted, became a cornerstone of modern approaches to complex systems science. David Ruelle's contributions, spanning several decades and intersecting diverse mathematical and physical disciplines, coalesced to forge this new paradigm. His early work in statistical mechanics, particularly the rigorous analysis of phase transitions and the mathematical foundations of equilibrium and non-equilibrium systems, instilled in him a deep appreciation for the power of abstract mathematical frameworks to describe collective behavior. This foundation in statistical physics provided a conceptual bedrock upon which his later explorations of dynamical systems would build. Transitioning into the burgeoning field of dynamical systems, Ruelle brought this rigorous perspective to bear on the problem of turbulence. Ruelle, alongside Forrest Takens, pursued a fundamentally mathematical explanation for the onset of chaotic fluid motion. Many researchers approached turbulence from phenomenological or computational angles. A groundbreaking work proposed that turbulence could arise from a finite dimensional strange attractor in the phase space of the fluid flow. This hypothesis challenged prevailing notions that turbulence required an infinite number of degrees of freedom. The Ruelle-Takens-Newhouse theorem, a landmark result, demonstrated how a simple sequence of bifurcations, specifically 3 bifurcations, could lead to quasi-periodic motion on a torus becoming unstable and giving way to dynamics on a strange attractor. This provided a concrete mathematical mechanism for the emergence of complex, seemingly random behavior from deterministic equations. The strange attractor concept possesses profound significance. It offered a geometrical and topological explanation for the unpredictability inherent in chaotic systems. Trajectories remain confined to a bounded intricate set in phase space exhibiting fractal properties. Ruelle's subsequent work focused on developing the mathematical tools necessary to characterize these strange attractors. He played a pivotal role in defining and understanding concepts such as the dimension of an attractor, providing methods like the correlation dimension to quantify its geometric complexity, and the Lyapunov exponents, which measure the average rate of divergence or convergence of nearby trajectories, offering a quantitative measure of chaos. Furthermore, his investigations into the statistical properties of chaotic systems, particularly the development of the thermodynamic formalism for dynamical systems, provided a framework for describing the distribution of points on a strange attractor using concepts analogous to those from statistical mechanics, including notions of entropy and pressure. This formalism allowed for a statistical description of long-term chaotic behavior, providing an alternative to precise long-term prediction of individual trajectories. The intellectual fusion he achieved merging ideas from statistical mechanics, ergodic theory, and dynamical systems theory proved exceptionally fertile. He demonstrated that the statistical properties of chaotic deterministic systems could be analyzed using tools originally developed for systems with vast numbers of particles subject to random influences. This revealed a profound underlying unity in the mathematical description of complexity, whether arising from deterministic chaos or statistical randomness. His work effectively legitimized the study of chaos and complexity within the highest echelons of mathematical physics, providing the rigorous language and analytical machinery enabling quantitative analysis. Ruelle's influence extended into numerous scientific and engineering disciplines. The mathematical framework he helped construct provided essential tools for researchers grappling with complex phenomena across numerous scientific and engineering disciplines. Climate scientists utilized the concepts of strange attractors and Lyapunov exponents to understand the inherent variability and predictability limits of the Earth's climate system. Neuroscientists applied dynamical systems theory, informed by Ruelle's work, to model complex activity of neural networks. Economists explore chaotic dynamics in financial markets, seeking patterns and predictability within apparent randomness, albeit with varying degrees of success. Fluid dynamicists found in strange attractors a compelling explanation for the intricate structures observed in turbulent flows. The abstract mathematical concepts he refined found concrete application in analyzing data from real-world complex systems, allowing researchers to identify signatures of chaos and characterize the underlying dynamics. He cultivated a research environment that valued deep mathematical insight applied to physically relevant problems. His writings, renowned for their clarity and elegance, served to educate and inspire generations of researchers, disseminating sophisticated concepts to a broad scientific community. He possessed a rare ability to distill complex ideas to their essence, making them accessible while maintaining their mathematical rigor. This pedagogical gift amplified the impact of his technical contributions, ensuring that his foundational work became widely understood and utilized. The enduring importance of Ruelle's legacy resides in several key areas. He demonstrated the power of a unified mathematical approach to understanding complexity across different domains. He provided the essential mathematical language and tools for the quantitative analysis of chaotic systems, establishing chaos as a subject of rigorous scientific inquiry. His work underscored the deep connections between seemingly disparate fields like statistical mechanics and dynamical systems, revealing underlying universal principles. Furthermore, Ruelle consistently emphasized the importance of mathematical proof and rigorous analysis in understanding physical phenomena. In an era where computational simulation and data analysis play increasingly dominant roles, his insistence on the foundational role of mathematical structure serves as a vital reminder of the need for theoretical grounding. Deep analytical work illuminated aspects of complex systems, revealing features simulation methods failed to capture. Despite the immense progress made in understanding chaotic and complex systems, thanks in large part to Ruelle's efforts, significant open questions persist. The precise mathematical description of turbulence, particularly in 3 dimensions, remains one of the grand challenges of physics and mathematics. The application of dynamical systems theory to biological and social systems, while promising, faces challenges related to model validation, data availability, and the inherent complexity of these systems. Connecting the abstract properties of strange attractors to observable, macroscopic phenomena continues to be an active area of research. David Ruelle's intellectual journey, moving from the fundamental particles of statistical mechanics to the global behavior of complex systems, exemplifies the profound interconnectedness of mathematical physics. His work provided a compass for navigating the intricate landscapes of chaos and complexity, offering both theoretical enlightenment and practical tools. The strange attractors he helped bring into sharp mathematical focus continue to serve as potent symbols of the deterministic origins of unpredictability and the intricate beauty hidden within disorder. His rigorous approach and deep insights have indelibly shaped our understanding of the complex world, leaving an indelible mark on the scientific landscape and inspiring future generations to explore the mathematical frontiers of complexity.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.